Hey, how are you guys doing today? I hope you're all doing amazing. So, we're back with day number 16 of Science and Cooking from Haute Cuisine to Soft Matter Science. It's a chemistry cooking class. We are learning a ton about basic cooking and stuff, well, more advanced cooking to be honest, from a scientific application. Currently, we should actually be at module 4, and so I don't know how it set back. Yeah, here's the module we're currently at. Let me go ahead and get chat up, make sure we have a video real quick, and then we'll get right into things. I hope you all are having an amazing week. Mine is going pretty dang good, and so I definitely don't have any complaints. I hope you guys are just kicking ass in your own personal lives and doing big things also. So, if you're interested in taking your own Harvard course online, you can using the link I put in the description below. You want to select the audit option. If you want to pay and receive the certificate for the course, they do allow that. I am currently auditing it, but for $249, we'd be allowed to receive a certificate. In many cases, the credits for the course, and that can go towards some of the programs and stuff like that are offered through Harvard or edX. And maybe you can even transfer those credits to your own institution. You'd want to check on that beforehand, right? So, Module 4's overview is going to be spherification, mini bars, atelier, crème. I have no idea what that is. Ceviche diffusion in eggs. And so we'll learn about that stuff. It says the lessons will include Jose Andres, founder of Think Food Group, and chef and owner of several restaurants, including Minibar, Gelio, and The Bazaar, about gelling agents and the remarkable ways he uses them in his cooking. Visiting Dominique Crenn of Atelier Crenn in San Francisco, who will make carrot jerky. I like normal jerky, I'll just be honest with that. A visit to America's Test Kitchen to learn the secrets of making coleslaw that doesn't get soggy. Science discussion on gelatinization and how unique properties of proteins and modernist thinkers make it possible. We'll also discuss the idea of random walk. I have no idea what that is, which is the underlying principle for diffusion and how it affects spherification, dehydration, and osmosis. The practical assignments are right here. Practice problems are actively and ungraded questions that are interspersed in the videos to encourage you to think about the material and develop your problem solving skills. Homework assignments are due at the end of the course. And for lab number 4, you will choose between 2 experiments. In the first, you can make a diffusion in eggs. I don't know about that, but maybe we do make a diffusion in eggs. Never done that before, so that sounds interesting. A classic dish that is used from diffusion of lime juice, H ions, into fish, okay, and the subsequent denaturization of fish protein to cook it. The finals are due for all lab assignments in this course at the end of the course. Here is the recommended reading. And the extra material we'll be hearing from Harold McGee about diffusion and gelatinization. We'll hear the history of gelling agents from Jose Andres, who I think is the guy that invented it, just to be honest. Then we'll see Jose Andres make some remarkable dishes using various gelling agents, including clementines, a strawberry, ravioli, coconut steam buns, and lemon chicken. All that sounds good, honestly. I don't know what clementines are, to be honest, but strawberry ravioli, interesting. I don't know. I've never had that, obviously, right? Lemon chicken, I think a lot of us have had. Learn how to make better scrambled egg from America's Test Kitchen. We all could improve on making our scrambled eggs better. Everybody likes better food. Hear about milk washing and technique for clearing liquids from Dave Arnold and see how it's used in preparing coffee rum. I can tell you I have no idea what they're talking about. I've never had coffee rum. So we won't probably get through all of that today, but we'll get through a chunk of it. I can't remember if this is one of the guys that speaks in Spanish. If so, I will pause it real quick after we get started and I'll read it to you and then we'll get back to it. But get ready. Hype video. We like hype. I'm gonna drink some coffee. Okay, let's get on with the video.
Hello, people of Harvard, people of the world. My name is Jose Andres. I am a chef. We are at Minibar. Minibar is very much the heart of everything I do.
Probably delicious food, guys.
I've been cooking since I was 14. I began working in kitchens in Barcelona, and especially in one of a restaurant called El Bulli, a restaurant that nobody knew back in the 80s, and where the chef was a young guy called Ferran Adrià. Almost 30 years later, I'm very proud to tell you that he's one of my best friends. He's my mentor and is the person I learned the most from, and is without a doubt the reason that we were able to put together this amazing physics class at Harvard. So, just for the record, I am a chef. We are chefs. We cook. We are not trying to be physicists. We are not trying to be scientists. We are only trying to make sure that the culinary world and the science world talk to each other.
This guy's passion for food, you know for damn sure his food is good. You know what I mean?
Everything you're going to be
that
learning
looked good. I don't even know what she's making.
Very clear explanation of everything that happens in cooking every day, in every kitchen, and through hundreds of years of history.
Okay, the hype is real.
Minibar every night, more than 30 courses, and quite frankly, probably many of the techniques we use here, you've been learning them through the class, and if not, you will. But
we have.
One of the classes I give every year is about gelation, and probably the star of gelation will be espherification. And here we are doing a lot of spheres. But this one is the cooler. Come here. When you're able to do espherification using a beautiful clam and kind of making sure that the natural juice of the clam will remain outside the meat of the clam, this is brilliant. And this is why I'm so happy about this class at Harvard, that for first time we've been able to take seriously the amazing connection between science and the food we eat. Before, we were in the dark. Today, I see light in the horizon. Today, we are far away more prepared. So, see you soon. Hasta pronto. Bye-bye.
I'm going to be honest, that dude's absolute love for
the
food,
few people that sometimes
it must be amazing. You know his food is going to be freaking good.
Well, take a look at this. We are grating Parmesan cheese. Wow, this is really molecular.
Okay, well, good to know. That's the start of it. We got a pretty dang good hype video right there. We're going to go right into about Dominique Crenn. I don't know Dominique Crenn. I'm sure she's an amazing chef because she's featured in Harvard's little cooking science thing. There's no way that she's not amazing. This is a spherification of some type of food. Honestly, I've seen a couple of spherification videos and stuff like that. There seems to be more than one way to do it, but let's find out how she's going to put it forward to us.
Hi, my name is Dominique Crène. I have a restaurant called Atelier Crène in San Francisco. Atelier means workshop, and Crène is my last name, but it's also my dad's last name. I don't know if I will call my restaurant a restaurant. It's a little bit more than that.
It's a restaurant.
In 2009, I had an accident that I almost lost my life to, and I kind of woke up in a way that I felt that maybe my life was going really fast. I wanted to open a place that, first of all, it was also an homage to my dad. My dad was a politician, but was also a painter. He taught me a lot about diversity, about art, about community, about bringing people together, and about sharing ideas with others. What I really love at Atelier Crène is not just the space in itself, it's also the people that are working with me. It's also important to have a platform and to be able to be inspired and inspire other people, and also to be probably a part of a change. It's not just what's going on in the climate, change. It's also about, the interaction with people and the community, and I want to be a part of it. I often say that food
These
is
dishes
art,
look
it's
interesting.
Also science. It's also a way of thinking.
Okay, interesting. I don't know what to think about that, but we'll click to the next person. These are going to be the people presenting in this section. So, if you want to discuss the materials from this module, please post questions and comments on Module 4 discussion. Gelatinization is a common phenomenon in cooking. Really, the only major requirement for forming a gel in cookings are a liquid of some kind and a polymer of some sort. Proteins in an egg white, for example, or the gelatin we add to water to make jello, marshmallows, or a number of other desserts. When these elements come together in just the right way, you can go from having a liquid to something that is no longer liquid, which now holds its shape due to the interaction between the polymer molecules. Even though it may not seem a solid as a substance like ice cream, we will start out by understanding two types of gelination process. Gel formed by proteins, as in examples above, and gels formed by carbohydrate polymers, as used in jams and jellies, vegetarian cuisine, and in modernist techniques like spherification. Collectively, these polymer systems in water are called hydrocolloids. Okay, hydrocolloids. Good to know. And cooks all over the world have been using them for many years to create a variety of different kinds of foods. Let's learn. Ready? Get set.
While wobbly might not sound like an appealing characteristic for food, it's the perfect description of the ideal texture of scrambled eggs. A quick blast of heat turns lightly beaten eggs from a runny liquid into a wobbly semi-solid, capable of holding its shape on the plate.
One of the most important phase transitions that occurs in cooking is gelation. So gelation occurs in many of the things that you might cook every day, and also occurs in some of the more esoteric types of cooking. It turns out that the unified way of thinking about all of these phenomena is to consider a phase diagram where what's going on is that there's a critical number of crosslinks in the gel, and that is what I would now like to explain to you. So the basic physics of this is the following. What you should imagine is that you have polymers. So polymers are long strands that are intermixed with each other, and you imagine that you have a meshwork of these strands that are basically interweaving each other. So they're just strands that can slide by each other and whatnot. So what you do when you form a gel is that you somehow stabilize the crosslinks between the strands. The crosslinks are the places where the strands overlap. And when you do that, you've changed what was initially a liquid, because the polymers could flow by each other, into a solid. And if the number of such crosslinks becomes high enough, you then create a gel. The gel, that we use when we cook, be it an egg or Jell-O or whatever else, there are different categories of how crosslinks can form. There are basically two categories, and in the first category, the polymers actually come from some protein component of the food. This is what happens with eggs. The proteins unfold because of heating, and then they stick to each other, forming crosslinks, whereas in the second category, there's some other binding agent that you're adding, some type of glue that causes the polymers to stick to each other. It turns out if you look through recipes involving what chefs call hydrocolloids, there are many different types of hydrocolloids. And these hydrocolloids can all be used to make gels, and they all have slightly different properties depending on what you're trying to make.
Here we use two techniques. We use agar-agar, and we use methyl cellulose. And again, forgive me, you're gonna say, what do you mean, you mess with corn on the cob? Kind of I did this video myself, it's not of the same quality. And I didn't choose the music. So take a look, guys. Water and methyl cellulose, okay? Remember that with the methyl cellulose, we were able to make the bread like. So we have that water there, methyl cellulose and water, that's it, we bring it to boil. There we have this gel-like texture. You see, very transparent, very translucent, gel-like. So here we have fresh corn juice and agar-agar. We get corn and we use the corn. And we only get the essence water of the fresh corn.
Okay.
And we mix the agar-agar with the corn. And you see these tapioca kind of straws? Take a look what we do. We put the water of corn with the agar-agar into those tubes. Here we get baby corn. And the part that is delicious is the corn kernel. I don't want the inside. So there we have baby corn kernels. And we mix the corn kernels with the methyl cellulose water base. And we get a paper, and with the help of a spatula, we are able to do this kind of very thin film of corn, baby corn kernels. So we get the gelatin with agar-agar of pure corn flour. We put it inside and we roll it. And right there, we make a baby corn. And now is the amazing thing. The agar-agar can be hot and the methyl cellulose actually gels when you apply heat. We are able to caramelize it, Maillard reaction, and at the same time we are able to achieve a film gel in the outside and the agar-agar inside gets warm and tasty and beautiful. We make a fresh corn kind of polenta. We put a little bit of bacon, we put a little bit of touches of butter. Because there
I would eat this just to know what it tastes like.
To bring the smokiness of the grill. We put corn nuts on top to intensify the crunchiness. Baby cilantro, a touch of lime. Ladies and gentlemen, corn on the cob.
Okay. Good to know. Interesting. That's definitely a different take on corn on the cob. I'm not really sure where to go with that. If you have questions as you're working through the practice problems, you can head over to Module 4 discussion forum. Scan through the post. Excuse me there. Scan through the post to see if you can find an answer there. Add a question yourself and see what others think. For quantitative practice problems and homework questions, sometimes will be useful. Use scientific notation for entering your answer. Review materials. We don't need to review that. Which of the following are examples of gelatinization? Check all that apply. Cooking an egg is. Jell-O is. Spherification is. Milkshake made with ice cream as only thickener. I think that this one would be gelatinization because we're thickening it. But I'm not 1,000,000% sure. These ones for sure are. Water and ice is not gelatinization. But that's what we could say. Which of the following can be considered a polymer? A protein is glucose. An amino acid chain, I'm pretty sure is, and I believe glucose is. What is the most abundant material in a gel? Does this still check all that apply? No. Oh, abundant material is probably still water. Are we thinking it is the polymers or water? I'm going to go with polymers. Let's click it. We'll find out in 1 second. Oh, we're wrong on all these. Let's ask to show answers and find out what it should be. The milkshake was. And only protein is on that. Okay. And liquids such as water was the correct answer. Okay. I got nervous. We'll click them all. Wait, the milkshake was not. Boom. Protein is. And liquids such as water. Submit again. Maybe we're right. Yep. Okay, so we've got that. Good to know, guys. We mentioned the gels are formed through crosslinks and discussed the energy U of INT of these crosslinks. But what precisely are the interactions of protein? And more directly, why do unfolded proteins stick to each other such as that they can form a gel? In this video, we'll explore the answer. Good to know. Let's explore that answer. Find out why that is. Prepare yourselves.
So the next question is, why is it that proteins are sticky when they unfold? So proteins, you will recall, are polymers, which are chains of amino acids. There are 20 different amino acids, and a protein is composed of some sequence of different amino acids. Depending on the protein, there will be a different sequence. Now, amino acids have different properties. This is a list of the 20 different amino acids that there are. They have names that range from aspartic acid to lysine to glutamine and so on. And each of these different amino acids has different chemical properties, but it also has different physical properties. And there are two types of physical properties that we want to focus on right now. So it's now possible, in the modern era, to find out what sequence of amino acids corresponds to any protein. So this is the sequence of amino acids that corresponds to chicken of albumin. Each of these letters refers to one of the amino acids that I just discussed, and that is the major component of egg whites. The amino acids have different properties, and I would like to start by focusing on two of them, because these are, in a certain sense, the most important for explaining why the different proteins stick to each other. There are some amino acids which are called hydrophilic, and there are others which are called hydrophobic. So a hydrophilic amino acid is one that likes water. Hydrophilic basically means that it likes water, whereas hydrophobic, it's phobic of hydro, namely water, doesn't like water. So if you put hydrophilic amino acids in water, they're perfectly happy. If you put hydrophobic amino acids in water, they're perfectly sad. They don't like being surrounded by water, but they have no choice. And their goal in life is really to cover themselves as much as possible so they don't have to contact with water. Now, they also don't like hydrophilic amino acids because hydrophilic amino acids like water. So essentially the deal is that if you have a protein which has a bunch of hydrophobic amino acids, what they will try to do is clump together and stay away from water as much as possible, whereas the hydrophilic amino acids are happy being near each other and being in the water. So with this as context, this picture right here is a toy model of a protein chain. So this protein chain has on it black dots and white dots. And for the sake of argument, let's say that the black dots are hydrophobic. So these are amino acids which don't like water, whereas the white dots are amino acids that do like water. So if I show you this string, then the question is what's going to happen to the string? Now, if the temperature is low, so that the protein doesn't want to jiggle around, it will try to fold into a compact clump, and it will do that by basically clumping all of the black dots, the hydrophobic amino acids, together so that they touch each other where they're happy, and it will also move them to the inside of the protein where they're away from the surface and thus don't want to touch water. You'll put all of the hydrophilic ones on the outside surface. They can contact water, and you shield the hydrophobic ones so that they don't touch the water. Now, of course, it's not possible to do this perfectly because they're also all attached to a string, so you might end up with some hydrophobic bits on the surface surface, but you try to minimize that as much as possible when you fold the water. And in fact, the principle of minimizing the free energy of the protein leads to this configuration as the most favorable state when you're at low temperatures.
Okay.
Now, when you're at high temperatures, then actually the entropy, starts to matter, and the protein unfolds. It unfolds because it likes jiggling around. Entropy, as we've discussed before when we were describing phase transitions, competes with energy and causes the protein to unfold. And once it does that, then all of these black hydrophobic amino acids that were initially buried inside are exposed and open for business. The business that they're in, of course, is sticking to other hydrophobic amino acids. And so what happens is that the different unfolded proteins bind to each other, causing cross-links, which is what forms the gel when you cook an egg. So we can see this in sort of toy models. It's also possible to do simulations of full proteins unfolding, and we just want to give you a little bit of dose of reality. So this is a simulation that was done.
Did you all know that's what happened when you cooked an egg?
A real protein that is unfolding. In which, and this is a molecular dynamics simulation that actually includes all of the forces and other things that we understand that are going on. And you see that so initially in its compact state, the protein has lots of helices in them and sort of bends, and these are characteristic structures that proteins tend to have. And when you heat it up, you see that the bends and everything go away and the protein unfolds. The hydrophobic residues are open for business, for sticking to others.
Okay, good to know. In the video, Dr. Bremen mentions unfolding as a phenomenon of entropy. In other words, for protein unfolding, we apply the same logic we have for phase transition. When the temperature of a system increases, the average motion of molecules increases. As in neat, folded protein starts to jiggle faster at high temperatures. It will spread out much like solid ice can jiggle into water. Thus, you can think about protein unfolding and denaturing as a breaking of smaller uint interactions of the unfolded protein, the same way we break the uint interactions between separate molecules. When many of these proteins unfold in the same place, new, stronger UNIT interactions can form between the different proteins to create very strong crosslinks. This is what leads to the solidification of foods like egg whites upon cooking, and is also part of why you can't uncook egg whites by simply reducing the temperature. I would never wanted to uncook an egg white, but good to know. Amino acids, locations in proteins. Ooh. Which of the amino acids below would you expect to be located on the outside of an unfolded protein? I don't honestly remember if the hydrophilic. Oh, but definitely not the oil-like property one. So we know the hydrophilic, but is hydrophilic positively charged or negatively charged? Okay. H2O is negative, right? I think it's the positively charged amino acids. Let me submit, but we could be wrong. Let me see the results. Oh, it's all three of these. And the negatives. So it doesn't even matter the charge. Good to know. Let's do that again. Boom, boom, boom. I knew it was these two. Well, I kind of thought it was these two, but I didn't realize that. So any of the hydrophilic amino acids, either negatively or positive charged, does not matter. Good to know, right? So are hydrophobic amino acids neutrally charged then? This makes me wonder. The chemical symbol for calcium ion 2, what does the 2 symbolize? It's the charge on the ion. That's what it is. Okay, boom. The chemical symbol for chlorine is, would a ion calcium 2 and a chloride ion attract or repel. They would attract each other. Boom. What did we do here? The charge on that is the charge on the calcium ion. What are they saying it is? Hold on 1 second. Let me just figure out. Oh, the number of electrons missing also. Okay, I didn't realize it was a double. I just read it and was like, boom, boom. I'm like, why? Why are we wrong? That's for sure correct. Big stress right there. Okay, we've got it. Okay, which of the following would have the strongest interaction with a positively charged amino acid like lysine? Oh shit, I don't know this. I don't know my acids. Okay, we've got positive charged lysine. Okay. Negatively charged, I believe it's going to be this one right there. Which of the following would have the strongest interaction with a negatively charged amino acid aspartate? And so we know this is a hydrophilic one. I believe it's going to be the positively charged one. Which of the following would have hydrophobic interactions with the hydrophobic amino acid phenylalanine? Hydrophobic ones like to be together, so it's going to be that one. Okay, let's click it. I think we're correct. Yes, thank God. That was a little bit nerve-wracking, right? Anybody else stressed out about those? Okay, we've talked about cooking proteins in a traditional sense by applying heat. However, it turns out there are other ways to cook proteins and make them unfold. Most of these methods require added common ingredients like acid or salt in order to affect the charges of protein molecules. We'll discuss how this works for pH in the video below. Let's listen to this. We'll find out how the pH affects these things.
So heating isn't the only way to cook an egg, and for that reason, it's interesting to think about other ways of even within the simple case of an egg, causing this protein unfolding and sticking transition. And so if you look at recipes, it turns out there are two other ways of actually causing transition in eggs. One is by changing salt concentration, by actually putting salt. That can affect the way that proteins fold. And the other is by changing the pH. And I want to start by demonstrating that in the simple recipe for a poached egg. In this recipe for a poached egg, if you look at the recipe, what it calls for is 1 tablespoon of vinegar and 4 very large eggs. So before you cook the eggs, you actually pour vinegar in the water. And then what the recipe says is really quite shocking for those of us who cook eggs on a regular basis, which is it tells you to boil them, but only for 2 to 3 minutes, which is a very short cooking time. And it claims that if you do that, that you still will be able to cook the egg. So it turns out that when you put vinegar in water, what you are actually doing is changing the pH of the solution. So you're changing the concentration of hydrogen ions in the solution. And in fact, you're increasing it quite dramatically when you put vinegar in the solutions. So why does this make a difference? So if we go back to the table of proteins and their properties, we so far have emphasized that there are some proteins that are hydrophobic and others that are hydrophilic. But there's one more important property that is worthy of mentioning, which is that some of the amino acids have negative charges. So aspartic acid and glutamic acid have negative electric charges, whereas arginine and lysine have positive electric charges. And electric charges, of course, are another way in which the amino acids on the protein can interact with each other. So if we go back to our little picture of proteins from before, the protein had black dots and white dots, which referred to hydrophobic and hydrophilic amino acids. But some of the amino acids are also going to have electrical charges. So some of them are going to have positive charges, some of them are going to have negative charges. Now, basically, the way that physics works is that like charges repel each other and unlike charges attract. So if you put a positive charge next to another positive charge, that causes a force that causes the thing to blow apart. Whereas if you put negative charges next to a positive charge, they'll like to come together. And there is, in fact, an electrostatic energy of the system, which is proportional to essentially the square of the charges that contribute to the free energy of the protein in solution. Now, of course, when the protein is folded up, it's already compensated for these charges, and when you heat it up, it unfolds, compensating again for the charges. But it turns out that one thing that you can do to sort of manipulate when proteins fold and unfold is to actually change the charges of the protein while they're in solution. And the way to do that is to change the pH of the medium. Because you see, it turns out that when we say that amino acid is charged, the charged amino acids change their charge depending on the pH that they're in. And so what we can do is, if we make the solution more acidic, therefore, we can make the charges more dramatic than they were before, and thus the proteins become easier to unfold. It is similarly the case that if we make the solution very basic, if we actually make the pH closer to 14, push it in the basic direction, then they also acquire a much more dramatically different charge than they would have otherwise. So that makes it much more likely to undergo from the uncooked transition to the cooked transition that we're all familiar with when we cook fish. So this, of course, raises the question, if you wanted to actually manipulate the pH of the solution, then how would you do it? And this is a table of different materials that one could imagine using when cooking, and with the typical values of pH that they have. So water, of course, pure water has a pH of 7. Vinegar, which is what we were using in the poached egg recipe, has a pH around 2.4, and lemon juice is around 2.2. Gastric juice, which is the material in your stomach, that's highly acidic. That has a pH around 1. On the more basic side, you could add toothpaste to the food that you're eating. That, it turns out, has a pH of around 9.9. Baking soda is a more common cooking ingredient. It has a pH of around 8.4, and so on and so forth. Now, the thing is, and one of the challenges when manipulating the pH while cooking, is that, of course, we don't just want to cause the proteins to unfold and coagulate. We also don't want to mess up the taste. And if any of you have ever had a spoonful of vinegar, you will note that it doesn't taste very good. So when you're adding vinegar to your egg, or for example, vinegar is one of the essential ingredients for cooking ricotta cheese, you have to make sure that you add only a little bit so that it doesn't affect the taste. And this is sort of one of the balances that we have in cooking between, on one hand, causing transitions by changing the acidity, and on the other hand, causing them with temperature. When we change the acidity, we also tend to affect taste.
Okay. Good to know. I don't really make a lot of poached eggs, so that's not something that's an issue for me, but it is good to know that stuff. So we're going to stop here today. We'll move forward with more of this, I believe, next Monday is when we'll hit this up. Tomorrow morning, I'm going to be working on Echoes of the Cosmic Veil, Book 2. That'll be fun. We'll try to knock out some more on Chapter 1. I'm only hitting this course on Mondays, Wednesdays, and Fridays from here on out, so that we can try to push forward on getting more of the novels out this year and stuff like that. Absolutely excited about this course and enjoying what we're learning. I hope you guys have a great weekend, or join me tomorrow while we work on knocking out some more of a novel. Peace, very best wishes, and you guys stay epic.